we have a example from the textbook here. We have 3 bungee cords and 3 bungee jumpers. Okay. And as you could kind of imagine, bungee jumper 3, their weight is going to have an impact on the stretch of these 3 bungee cords. Okay. Bungee jumper 2, their weight is only going to affect bungee cord 2 and bungee cord 1, and the weight of bungee jumper 1 will only impact the stretching of bungee cord 1. Okay. But the thing to note is the weight of bungee jumper 1, while it's only going to stretch this one here, but because the top one stretches, it's going to move these 2 bungee jumpers down. Okay. And again, if we were to think about bungee jumper 2, their weight, okay, well, their weight is going to have an impact again on stretching this bungee and this bungee. Okay. But even though they don't stretch the 3rd bungee, it's going to result in the 3rd bungee jumper still scooting down. Okay. If the first 2 cords stretch, the 3rd one, even though it won't stretch, the 3rd bungee jumper will move down. Okay. Okay. Now, this X1, X2, and X3 are just the displacement of each bungee jumper. Okay. And by displacement, we mean if these bungee jumpers were massless, you know, where would each one of those nodes be? Okay. Let me maybe try and sketch something like that in here. So yeah, if each one of these bungee jumpers were massless, okay, then the displacement would just be 0, okay, for all of these. And the question is when we do assign masses or weights to each one of these bungee jumpers, how far is it going to move each one of these bungee jumpers down? Okay, that's the question here. Okay. Now, we have a system of equations here that can be used to actually determine the displacement of each one of these bungee jumpers. Okay. And the things that you would need to input into this are the, let me get a pen here. You'd need the K's, which are spring constants. And these are spring constants from Hooke's law. The other thing you have, again, are the masses of each bungee jumper. And with the G next to it, that really means that these are the weights of each bungee jumper. Okay. And again, the X's are the displacements of each bungee jumper. Okay. And well, we have the corresponding spring constants here, the bungee jumper masses. Okay. And this allowed us to set up this system of equations down here. Okay. That's all that's going on here so far. Okay. Now, the next thing is we could solve this system of equations using the inverse of the matrix A, and it would result in this kind of messy looking thing here. But if we were to split it up a little bit, okay, in fact, putting this in what we call vector form, okay, it actually tells us a little more. Okay? And it is what I mean by that is the entries in the inverse of matrix A actually play a significant role here. They can help us interpret what's going on a little bit. Okay? And so in order to do that, I want to do a concrete example. Okay? So I've actually went and computed A inverse here for us. It is this matrix right here. And then I've written it in this vector form down here in hopes that it will help us interpret, again, what is going on. All right, and I just want to remind you, in our example, the B's, or the B vector, was just the vector of all of the bungee jumpers' weights. Okay? But when we write it in this form, is what we can see is if bungee jumper 1, their weight, if it were to increase by 1, it would result in stretching bungee 1 an extra 0.02 meters. And that would result in the other 2 bungee jumpers moving down the same distance. Even though this was the only one to stretch from this increased weight here of bungee jumper 1, it's still going to scoot down these other 2 bungee jumpers that same distance, even though their bungee cord did not stretch. Okay? It's kind of interesting. Let's see what the implications of this one here would be. So if you were to increase the weight of bungee jumper 2, okay, well, that force would be felt by this first bungee cord. And you can see that that increase of 1 Newton of force results in displacing bungee jumper 1 the same amount, okay, which is expected. It's the same increase in force that's felt by that cord. However, because this happened here at bungee jumper 2, it's going to stretch both bungee cord 2 and bungee cord 1. Okay. And so again, bungee jumper 1 is displaced 0.02 meters. Bungee jumper 2 is displaced 0.03 meters. And you'll notice that bungee jumper 3 is displaced the same amount as bungee jumper 2. Okay? And that's because, again, only these 2 cords stretched. So bungee jumper 3 just went down the same distance that bungee jumper 2 went. Okay. And then one last one here. Okay. Again, if we were to add just 1 Newton of force to bungee jumper 3, it would result in causing the same stress on bungee cord 1 and bungee cord 2 as in the previous 2 thought experiments. And that's why you can see the displacement is the same for bungee jumper 2 and bungee jumper 1. Okay. But bungee jumper 3, okay, is also going to stretch their bungee cord. Okay. So we're seeing a different displacement here for all 3. Okay. For all 3, because all 3 of the bungee cords are experiencing an increase in force. I'd like us to do one last thing here, and that is to really answer this highlighted question. How much farther, or determine how much farther the third jumper would move downward if additional forces of 10, 50, and 20 newtons were applied to the first, second, and third jumpers respectively. Okay. So all we'd have to really think about here, and let's maybe call it delta x3. Let's go ahead and write that down, delta x3. Well, this should be equivalent to the change in the force for bungee jumper 1, so that's 10. And again, we're looking at x3 here, so we're really looking at this last line in every single one of these vectors. Okay. All right. And then, so that should be times 0.02 plus the change in force for the second bungee jumper, so that'd be 50. And lastly, the change in force for the third bungee jumper is supposed to be 20. Okay. And the number associated with that is the 0.05. Okay. So this is telling us how much more bungee jumper 3 will be displaced based on this increase in B1. B2 times this number is going to give us how much bungee jumper 3 is going to be displaced by this change in force with the second bungee jumper. And then this last thing we calculate, B3 times 0.05, this is going to give us the change in displacement for bungee jumper 3 based on this change of 20 newtons of force on bungee jumper 3. Okay? It's just we've added each one of these components here together. Okay? And so if we go ahead and multiply all this together, we're going to get about 2.7 meters. So yeah, our inverse matrix actually tells us more than you might